Didn't you do like the pacer?
Okay, so did we do this one yesterday where we talked about the melting points and boiling points and we explained why? I think we did. We talked about how the magnesium and the oxygen have a bigger charge, and therefore their attractions are going to be stronger than with the sodium chloride. Then we were sitting down, we were getting ready to start our discussion of hybridization. That's where we had kind of left off, and that's where I wanted to pick up today, was talking about hybridization. So let me...
It smells like a tea. A tea bag. No, my chapstick.
So remember, we talked about hybridization earlier this year. What hybridization is taking an s orbital and a p orbital, and we end up hybridizing it and making it into an sp orbital. Okay, so if we're looking at something like carbon dioxide, okay, when we draw this structure out, we have carbon here, we have an oxygen here, and this is double bonded. And then we have lone pairs of electrons around the oxygens. And when we're doing this, remember, we're trying to get the lowest formal charge for this possible. So that's what this structure is. We talked about formal charge. Remember, formal charge is should minus has. Remember that? So oxygen should have how many valence electrons? 6 valence electrons. It has 1, 2. Remember, the lines would count as 1 when we're doing should minus has. So 1, 2, 3, 4, 5, 6. Its formal charge is 0. Carbon should have 4. It has 4. 1, 2, 3, 4. When we're doing should minus has, each line counts as 1. And then the oxygen here again is 0. For the overall formal charge on the molecule is 0. Now, if we're talking about in terms of hybridization, how this is hybridized, now that we know that the structure is built properly, we're going to look at our oxygen here. And the easy way that I told you to figure out what the hybridization was, it's going to be sp something, and there's going to be a number here if it's 2 or 3. And I told you, when you have these, any double or triple bond, you're going to count that line as you're going to pull down 1 finger. So I told you to hold up 3 fingers, and for each one of these, pull 1 down. So for oxygen, its hybridization, I'm going to pull 1 finger down. So its hybridization is going to be sp2. Remember that? Oxygen's hybridization. I pull a finger down for this pi bond. So it's sp2. For carbon, I'm going to pull a finger down for this guy, and I'm going to pull 1 down for this guy. Oh, flipped me off. Okay. So,
oh my God.
So this ends up being sp. All right. We don't put the 1 up there. It's like algebra. You don't put the 1 in front. Okay. So this is sp2 for this guy. Now, how does that work? The way that we draw these, if they're never ever going to ask you to do this, okay? But we know with this happening, remember, we have 3 p orbitals. We have an s orbital. Sometimes we hybridize these, sometimes we don't. Anytime you have a double bond or a triple bond, you have to leave one of these p's open for that bond. So for the oxygen, you're going to take these 2 p orbitals and you're going to hybridize them. That's where that 2 comes from. This p orbital here has to remain a p orbital. We cannot hybridize it. Because to have a pi bond, you have to have a p orbital. So for the oxygen, we end up having this. Okay? Oh, shoot. For both the oxygens, it's going to look like this. For the carbon, then, it's going to have your p orbital here, okay? And then it's going to have a p orbital here and here for those. So it has to leave these as p orbitals, one for this and one for this. Okay?
So one is left to hybridize?
Just one p orbital, so that's why it's sp. There's only one p that gets hybridized.
And that like the double bond?
This is, you have to have one of these open for that, and you have to have one of these open for that.
What does those?
Okay, so this is the way that looks. All right, I'm going to draw this oxygen here. All right, so this oxygen would have two sp orbitals, or three sp orbitals, because you're going to have three come out of here. So you're going to have an sp, an sp, an sp, and a p. So those are going to be your four orbitals coming out of this for your oxygen. So you're going to have one sp orbital coming out this way, one coming out this way, and one coming out this way. These two right here are going to have your lone pairs of electrons in them. That's these two right here. Okay. This one then is going to hook up with this carbon. Now this carbon has two sp orbitals. Okay. So because it's got p that it's hybridized, so you've got this and this coming out of this hybridization. So these two become these two. Okay. That then is you're going to have your carbon here. It's going to come over. It's going to have a sigma bond here. And it's going to have another sp orbital over here. And that's going to hook up with another oxygen. Come on, why are you not letting me? Okay, is it like locked up? There we go. It was just locked up. Okay. So I'm going to draw my other oxygen over here. It's going to be identical, but kind of a mirror image of this. Does that make sense? So that oxygen is going to be over here. That is a sigma bond. Sigma bonds are end to end. I've got my lone pair of electrons here and a lone pair of electrons here.
So what is the double bond?
I'm getting there. Okay. So these are my sigma bonds right here. My pi bonds then are going to be coming in. I have to have p orbitals for those. Okay. So I've got a pi from this guy coming in. And remember, these are p orbitals. So they're going to be like here. And then I'm going to have another pi coming in from the carbon here. And they are going to be side to side. So these are my pi bonds. That's my double bond. My double bond consists of my sigma here, which is underneath now, and my pi bond here. And then I have a duplication of that over here. Okay, I've got my sigma underneath there, and now I'm going to end up covering it up with this guy. Here is my, oh, that should have changed colors. Sorry. Okay, but this one came from the oxygen. Does that make sense? Even though I didn't color code it.
Yeah.
So one of the pipe orbitals come from each.
Huh?
So one pi orbital comes from each.
Yep. Yep. And that's why I have one pi bond comes, one p comes from each. One from the oxygen, one from the carbon. That one from that oxygen, one from that carbon, and that's going to bond. So there is your sigma bond, or your pi bond, I mean. And then your sigma bond is underneath that where it was end to end coming in.
And so from that we get the sp2 hybridization.
you count how many P's hybridized. So for this one, you had 2 P's that hybridized to give you 3 of these. So you had 1 here, 1 here, and 1 here. But you had 2 P orbitals that did that.
2 p orbitals and then get 3 hybridized.
Because you've got an S, a P, and a P. 1, 2, 3, 1, 2, 3. Good? Good? Make sense? Okay. All right. So that's how that bonding kind of works. All right. Now, the easy way to do this, though, is to hold up 3 fingers, take 1 down for each double or triple bond.
No, there's none.
So how many fingers do you have?
3.
3. So is this sp3?
Oh my God.
Okay.
This is a drawing I made.
All right. Which of the following has polar bonds but is a non-polar molecule?
CCl4.
Okay. So let's look at this guy and see what is the case there. Oxygen ends up looking like this. Is this symmetrical? Yes. This is a non-polar. Okay, and it's non-polar bond as well, because your electronegativity is 3.5 minus 3.5, which is 0. So this is actually a non-polar bond and a non-polar molecule. NH3. So nitrogen is 4. So 3. So 3. And hydrogen is 2.1. I told you guys you needed to memorize those couple electronegativities yesterday. Okay. So this is a 3 minus 2.1. So what kind of bond here? 0.9. What kind of bond is this?
Polar.
It's polar, covalent, because it's a metal or 2 nonmetals, and it's polar because of the electronegativity difference. Is this a polar molecule or not?
No, it's not polar. Yes, it is. It's polar.
Anytime you have lone pairs of electrons on the central atom, it is polar. So it's a polar bond and a polar molecule. All right, HF. This is 4 minus 2.1. It's between 2 nonmetals, so it is covalent. Covalent what?
Polar.
Polar covalent, very polar covalent. And what kind of molecule is it?
What do you mean?
The
Polar.
bond is polar.
Oh.
What kind of molecule is it?
Polar.
Is it polar or non-polar?
Polar.
Polar molecule. There is a heavy presence of electrons here versus here. All right, H2CO, so CO, H, H. All right. I've got 2.1. So my bond here is 0.1. That bond would end up being
Polar. Non-polar.
non-polar. It's 0.1. Okay. This bond here is 3.5 minus 2.5.
That's polar.
That is a polar bond. Is this a polar molecule or not? Yes, this is a polar molecule. You've got a concentration here of charge on this side. All right, now we've got C, Cl. I'm fairly certain Cl is 3.5. I wouldn't swear to it, but I'm fairly confident of that. This is 2.5. So this is a 1.0 difference. What kind of bond?
Polar.
Polar.
But it's non-polar.
And what kind of molecule? Nonpolar. Okay, and I believe that was the answer to the question, which of the following is a polar bond but a nonpolar molecule, and that is correct, and D is, or E is our answer. Okay, questions on that? All right, tetrahedral shape. You guys were supposed to memorize your shapes on these. Okay, so let's see here. We've got our NH3. Ah, shoot. Come on. NH. Okay, what is my shape here?
Tetrahedral.
This one. Trigonal pyramidal. Okay, what is this?
Linear. Boom.
Bent. What is this? Trigonal planar. This is tetrahedral. And this MK is linear.
It's D.
What about trigonal? What about tetrahedral?
All right, covalent compounds, continuing with that, we've got graphite sheets of carbon are bonded together and stacked on top of each other. When you are writing with a pencil, what you're doing is you're sloughing off sheets of that graphite. It's coming across as sheets, and that's what you're laying down on the paper. Those are arranged in this shape, but they have no interaction. I mean, they have a little bit of interaction, but for the most part, there's no bonds between these. So that's why it's easy to break pencil lead, for example. Diamond, though, has between these sheets, between this arrangement, it has these connections. And that's one of the reasons why diamond is so much more resistant to being broken apart. Okay, IMFs. This is a big part of
18 to 22?
Yeah, like this is a massive part of your test. This is why in honors chem or pre-AP, I spend so much time on this because it's important that you understand it when you come in here, and then when you're here, you get a deeper understanding of it. All right. Electrostatic forces then are going to exist between molecules as well as atoms or ions, and breaking those intermolecular forces is going to require energy. Remember, when you're breaking intermolecular forces, that is a physical change. Okay? When you're reducing or increasing these, that is a physical change. So intermolecular forces listed from weakest to strongest. Thus, the boiling point and vapor pressure of a molecule can be ordered based on IMF strength. So dispersion, which is your induced dipole, or your London dispersion forces, your LDF, is caused by a distortion in the electron cloud. The more surface area, the more polarizable. Remember, that is a word that they love to hear you use properly. The stronger the dispersion force. So if you have a boiling point, when you look at these, this trend occurs. So these are all nonpolar molecules, nonpolar bonds. Fluorine and chlorine at room temperature are gases. Bromine, same structure. This is a liquid at room temperature. This guy is a solid. It all has to do with London dispersion forces. So they talk about increasing the molecular mass, but it's not really the molecular mass that you need to be thinking about. It's the number of
Electrons.
electrons. Because if you increase the number of electrons, the molecule becomes more polarizable, leading to increased LDFs, which increases the boiling and melting point of the substance. Okay? Memorize those phrases. Dipole-induced dipole then occurs when a polar molecule and a nonpolar molecule come near one another. This will distort this and create an interaction. Dipole-dipole then is going to occur between polar molecules, where the positive end of the molecule is attracted to the negative end of another molecule. And then your hydrogen bonding, remember, you need to be on the phone. You have to have a hydrogen connected to one of the other, something on the phone. That something on the phone needs to have lone pairs of electrons. That is going to cause then this hydrogen bonding to occur between the fluorine of this molecule and the hydrogen of this one. This end of the molecule is going to be negative. This end is positive. And so the negative end of this one is going to be attracted to the positive end of this one. That makes sense?
Yes.
Okay. All right. Intermolecular versus intramolecular. Intermolecular means that it is occurring between molecules. Like the interstate is between states. When we break these intermolecular forces, we have a physical change occur. If you break intramolecular forces, then you have a chemical change. These are your covalent and ionic bonds. These are within a molecule. So for example, if we have water, okay, we've got our water. If I break this bond here, that is a chemical change. This is a chemical change. If I break that water, okay, that is intramolecular. It is a physical or a chemical change. If I have another water molecule nearby, okay, and that oxygen of that water molecule is getting attracted to the hydrogen here, and I break this, that is an intermolecular force. That is a physical change. All phase changes are physical changes. All phase changes are physical changes. We talked about vapor pressure yesterday. Viscosity runs into the same thing. Increased IMFs equal increased viscosity. High surface tension has high IMF. Low vapor pressure has high IMF. Do you remember from yesterday what vapor pressure is? You want me to go over it again?
The way it evaporates on its own.
Yep. So things that have low vapor pressure don't evaporate very easily. And what the vapor pressure comes from is when that is in a closed container, remember some of that liquid is going to evaporate. If you have high IMFs, very little of that is going to evaporate, which means that it's going to put very little pressure against the sides of the container. If you are asked to rank molecules in order of boiling point, melting point, viscosity, surface tension, vapor pressure, what they're actually asking you is to rank them in terms of intermolecular forces. So look for the molecules with hydrogen bonding. If they have hydrogen bonding, they're going to have high intermolecular forces. Look for molecules with dipoles next. They're going to have the stronger intermolecular forces. And then look for the larger molecules when you're looking at LDFs. Okay, so again, this is their depiction of that. This is an intermolecular right here. Intramolecular is going to be here. It's between atoms. So intramolecular is between atoms. Intermolecular is between molecules. All right, London dispersion forces, noble gases, and nonpolar gases. Which of the following would have the highest boiling point and why? Yep. C is the correct answer. Okay. This will have more electrons, therefore it's more polarizable, leading to higher IMFs. Okay. Remember, it is the increase in the number of electrons that make it more polarizable, not the increase in mass. Okay. I have been over this with you many times. I would jump up and down if I had to.
Do it.
No. Okay. Hydrogen bonding then. Again, it is between, you've got to have, and this is your, DNA. Okay. So you have hydrogen attached to a nitrogen that has at least one lone pair of electrons. Okay, lone pair of electrons here. They just didn't depict it. It's the nitrogen of one molecule with the hydrogen of another molecule. Hydrogen bonding is not this. This is not hydrogen bonding. Okay, this is not hydrogen bonding. Here you've got a hydrogen attached to a nitrogen with lone pairs of electrons, and then you've got an oxygen over here. This is hydrogen bonding. Hydrogen bonds just want to have fun.
So they attached to the
Polar molecule over here. Yep.
on both sides. So the hydrogen second.
Well, this hydrogen here is attached to a nitrogen. This is an intramolecular bond. This is a covalent bond. Okay. This is an intramolecular bond. These are two completely different molecules here. This is one molecule, and this is another molecule. This is your hydrogen bonding. Which of the following substance would have the highest vapor pressure and why?
I had B. Because it is the smallest molecule.
Highest vapor pressure. Yeah, so
Which is the least.
I hope you are. Practice 10 minutes of mindfulness every day. Pacific Sunwear. Peace, love, and
so 4 times 35.5 is what? 35.5 times 4 plus 12. So molecular mass, this is, of course, it's just a single atom, so it's nonpolar here. But it, remember, its molecular mass is 200.1. This has hydrogen bonding in it, not just, guys, this has hydrogen bonding, dipole, and it has LDF. This one is a nonpolar molecule, just like this one was, but its mass, molecular mass, is 154. Which one has more electrons? This guy's going to have more electrons up here. This is the 154 here. Okay, so this is going to be more polarizable. And then this guy,
Making it like in the water.
It was 2
I don't
years
know.
ago.
so this guy is going to be 142. He's going to be nonpolar as well. Oh, why would it be? I don't know. Oh, because it's still much smaller. This one is going to be, when you draw it out, 3, 4, it's going to be spread out so far compared to this guy. Their masses are not really that massively different. Does that make sense? There's not a lot of difference here. There's only like 12 electrons. But this guy is going to be so spread out by the time you draw 10 of these across here, compared to this where it's just doot, 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 doot. Make sense? Okay, yeah, I had to sit there and think about that for a second too. Yeah, shape.
Because it was expired.
Okay.
Brain what?
All right, which of the following are broken when water boils?
Okay, I guessed on this one.
Hydrogen bomb.
Hydrogen. No, not covalent.
No.
Hydrogen.
Bad. Bad little.
Bad girl. What a dumb guess. It's hydrogen.
I had hydrogen.
All of
Yes, I knew it.
all of these, because these are IMFs.
That was a trick.
Okay.
You were going to present.
Sorry, I was just saying random.
Yeah, these are your IMFs. Yeah.
Chemistry.
Water has all 3 of those IMFs. They didn't say which one of these. They said which are.
Oh.
We are. Privately. I cannot get out of the shoes. I can't be friends with such a person.
I'm sitting there with a question
I don't understand
and I
the
saw
difference. I don't understand the difference between D and J. I guess I know the difference. I don't know which one answers the question.
in the minute after I got the.
Did I stop my recording? Hold on, let me stop it.